So welcome to today's presentation on the structure and properties of matter. And we're going to, these are the objectives of the day. We're going to look at the clear distinction between streamline and the turbulent flow. We're going to discuss the physical mechanism of viscosity and derive the equation of motion for an incompressible, non-viscous, and a streamlined fluid flow. Then we shall look at some applications of Bernoulli's equation. And we're also going to look at the Poiseuille's equation at the tail end of our discussion. So basically, laminar flow, or what you call the streamline flow, it is the kind of flow where which is continuous and very steady, and you can be able to see that the layers, the particles are able to move in distinct layers, and they have different velocities, but the velocity is low, and therefore there is an orderly kind of flow. But a turbulent flow, you can be able to see what we call vortices, they actually set in. We also call them eddies, which now makes the flow to be turbulent, and this reduces the energy because there's a lot of frictional force, or what you call viscosity, inside the flow of the fluid. So you can be able to see some differences between the laminar flow. For instance, the laminar flow is smooth, while the turbulent flow, the velocity fluctuates, and it is highly disordered kind of motion. For the laminar flow, the path line, each particles are parallel to each other, but the turbulent flow, the particles have an irregular path line. The laminar flow has a low velocity, the turbulent flow has a high velocity. So you can be able to see that, for example, the velocity profile shown, it shows a parabolic curve. For instance, you can be able to see this curve which you're talking about here. It is parabolic, whereby the particles which are at the middle of the pipe, because they have lowest friction or viscosity, they are moving at a relatively higher velocity than the particles which are closer to the container, which are moving at a lower velocity. So these are parabolic kind of curve, but the velocity profile of a turbulent flow, it has a logarithmic kind of a curve. So we can be able to use Newton's law to be able to come up with the law of viscosity, whereby we are looking at the velocity gradient, which will be given by du dz, where dz is the height of that liquid column there, and then our u will be the velocity. So basically, the du dz will be able to give us that change in velocity per unit change in that height of the liquid column is actually proportional to what you call the force per unit area. So you're talking about force per unit area, which is represented by a torque. It's directly proportional to the change in velocity or the change in the height of that liquid profile. And the equation is given. It's a very important equation. We shall again revisit it much later. But this is Newton's law of viscosity, where this symbol here, mu, represents the coefficient of viscosity, and the units you can be able to see them here. So it's basically the force per unit area, which is now when you remove the proportionality sign, you can be able to get it will be du dz. The factors which lead to the formation of eddies, all vortices, one of them is viscosity, another one is density, and then also the dimension of the channel in which the liquid is flowing. So the velocity at which the turbulence sets in is called the critical velocity. And the Reynolds assumed that the critical velocity is a function of those three factors which you have listed here, mu, rho, and r. So using dimensional analysis, you can be able to show that critical velocity will be given by those three variables, where we put in subscripts as some variables, and then we use dimensional analysis, whereby the dimensions of velocity, it is L divided by T. And also now K is our constant here. So using dimensional analysis, you can be able to find the values of where we equate the dimensions on the left-hand side and the dimensions on the right-hand side. And we can be able to get the values of the variables as 1, -1, and -1, giving us an equation whereby the critical velocity will be given by K, which is just a constant. Then we have what we call mu divided by rho r. So what is the physical now mechanism of viscosity? Because basically viscosity is the friction of force in liquids. One of the mechanisms is that there is a net momentum transport from regions of high velocity to regions of low velocity. So as we're able to see that the curve of a streamline flow, it is parabolic. Therefore, there's going to be a kind of a momentum transport, and the momentum is basically the product of velocity and the mass of that particular object. So this force is the viscous shear stress, and the rate at which the momentum transfer takes place, it is dependent on the rate at which the molecules move across the fluid layers. So as you can be able to see in this diagram here, it is that the particles can be able to move from one layer to another. But since the velocities are not the same, then there is a kind of transfer of momentum between the layers. And now when you talk about turbulent flow, then here we consider the macroscopic tanks. That means you look at the liquid from a large scale point of view, and therefore the momentum, the larger mass of the macroscopic elements of the fluid transport more energy and the momentum than the individual molecules. So when turbulence sets in, we look at the flow from a macroscopic point of view. And so large mass, the larger masses of the macroscopic elements, they're able to transport more energy and momentum than the individual molecules. So there's going to be a greater change in momentum in a turbulent flow as opposed to a streamline flow. Next, we're going to look at the equation of continuity. The equation of continuity is a very important equation which tries to relate the volume of flow in a particular cross-sectional area compared to another cross-sectional area. So for example, you can see here we have A1 and A2. These are our cross-sectional areas. So basically the equation of continuity states that the flow, the liquid which is able to move from A1 should be able to be the same liquid which comes into A2. The volume flux per se at A1 should be equal to A2, as long as the liquid is has a streamline kind of flow and it is non-viscous and it is not compressible. So therefore, if we equate the volume flux at region A1 and region A2, you can be able to see that the volume, the flow rate at region A1 is A1 V1 times change in time, and the volume flow rate at region 2 here will be A1 V2 delta T. So if we equate these two here, we can be able to show that A1 V1 is actually equal to A2 V2. And we can also talk about the mass flux, where we can just add density to that particular formula. So that equation of continuity, it's actually it's used to solve problems together with Bernoulli's equation. We're going to talk about Bernoulli's equation as an equation which relates pressure, speed, and the height at any 2 points within an ideal fluid. It is actually given by this formula here. And this formula comes from the conservation of energy. That basically the energy, we know that energy cannot be created nor destroyed. It can only be transferred from one form into another. So in this case, you're seeing the pressure, the initial pressure, initial kinetic energy per unit volume, initial potential energy per unit volume will be equal to a pressure change at a new point. And you can be able to see this is the new kinetic energy per unit volume and the new potential energy per unit volume. So basically, these are very important. This one here is just the conservation of energy. that when one of the parameters change, the others are going to change in such a way that the total energy of the fluid is actually conserved. So basically, as you have said, it is said that in a steady ideal flow of an incompressible fluid, the total energy at a point of the fluid is constant. And so you can be able to see here when you talk about, because the equation of kinetic energy is a half times mass times the square of the velocity. But since this is per unit volume, mass or volume will be able to give you density. So that is why here we have the density, here we have the velocity. So there's an example which you have here concerning the Bernoulli's equation. You're given water at a gauge pressure. Yes, Kevin Joroge can ask a question. Yes, Kevin, unmute yourself and ask a question. Yes, Kevin. Kevin, I cannot be able, maybe you can type it. I can be able to read out your question even as we progress. So Kevin, please, I can see your audio is off. So if you can be able to type your question, then I'm sure you can be able to respond to it even as we progress. So just feel free to go ahead and ask your question even as we progress. So as I was saying that I believe the equation which you're trying to explain here, that is the Bernoulli's equation. Probably you're trying to ask something related to this equation here. So when you get your question, be able to respond appropriately. So there's an example which you're given here, just as an application of Bernoulli's equation. Water at a gauge pressure of 3.8 atmospheres. You'll be able to read this question here at a speed of 0.06. So this is the initial velocity and a diameter. So you can be able to, through a pipe, which is 5.0 centimeters in diameter, the pipe tapers down to 2.6. So you can be able to see the height of this pipe, all the diameter here is different from this second one over here. Calculate the flow velocity and the gauge pressure in such a pipe on the top floor. Assume there is no branching of the pipe and ignore viscosity. So the first part of that equation of getting the velocity, we can use the equation of continuity. A1 V1 is equals to A2 V2. Making V2 to be the subject, you can be able to supply in the values and get a velocity of 2.2 meters per second. Then we pick this velocity, insert it in Bernoulli's equation. Bernoulli's equation, you can see it, it's over here. We have already gotten the value of V2. So and now we are looking for pressure 2. We are given pressure 1 as 3.8 atmospheres. So if we substitute these values here, we can be able to get the value of pressure 2 as 2.8 times 10 raised to power 5 pascals. So you can be able to see in this problem, we have just applied both the equation of continuity, and we have also applied the Bernoulli's equation. Somebody has lifted a hand. Yes. Just unmute yourself and ask your question. Who is this?
Boniface, teacher.
Yes, please ask your question.
I was asking, will you mind if you repeat the formula?
The formula of Bernoulli's equation.
Yeah, because I was attending the class while you were that side.
Okay, now the Bernoulli's equation, basically it's an equation which is based on the conservation of energy. And we know that energy cannot be created nor destroyed, but it can be converted from one form to another. And when you're talking about mechanical energy, we are basically looking at two forms of energy. The one is potential energy, but here we are talking about potential energy per unit volume. So you know that potential energy is given as mgh. So if you divide by volume there, mass over volume will give you density. And then you also have kinetic energy here per unit volume. The kinetic energy is half mv squared. So mass divided by volume gives you density. So you can be able to see here, we have a half times density times V1 squared. So these are the two main forms of energy. We are basically adding a third form of energy, which is pressure energy. You know that when a liquid is actually flowing, there's a change in pressure. So we have pressure 1 and we have pressure 2. So basically, we are saying that the initial energy here should be able to be equal to the final energy from the principle of conservation of energy. So this is potential energy per unit volume, kinetic energy per unit volume, and on this side here we have pressure. Is that okay?
Yeah, okay, sir.
Good. So just allow us to progress after looking at that equation there. We have some other examples of applications of Bernoulli's equation. And one of them is the flow of a liquid through a wide tank. So if you can be able to see this tank with a height here given as H1, and then there's a small opening at the end there, almost at the bottom at point Y, and then water is filled to a liquid of H1. So at point X, the pressure, velocity, and position are respectively given as P1, that is the pressure, velocity 1. So, and at some point you're going to see that since the velocity, the liquid is at rest in a tank, then velocity 1 can be approximated to 0. And then we have height 1. So height 1 will be given by this height, which is the height of the liquid or inside the tank. So if we insert these values, and also at the bottom here, we have velocity 2. Where velocity 2 is now the velocity at which the liquid is coming out of this tap. We have height 2, which is the height from the bottom. And we have also pressure 2. That is the pressure at which the liquid is coming out of the tube here. So if we can be able to insert these values in the Bernoulli's equation, we can be able to get. So basically, you can be able to see here what you have basically done. On the left-hand side, we have divided through by pressure. So you're going to have V1 squared divided by 2 plus, this is pressure 1 divided by density. Rather, we have divided by density on the left-hand side and also on the right-hand side. So we are going to have, Bernoulli's equation can be rewritten in this form here. And you can be able to see now here we have, this is gravity multiplied by height 1. And on the right-hand side, you can also be able to see we have V2 squared over 2. We have divided all through by the density. So we have said velocity 1 can be approximated to 0 because of the fact that now the change at which the water is decreasing, it's very, very small compared to the larger side. So you can be able to see, I've made an assumption here that since V1, the velocity V1 relative to V2, it's much, much smaller. So V1 can be set up to 0 so that the equation now becomes 0 plus. Here we have A over rho here. We are talking about where our A now it's basically the cross-sectional area of that tank, and then rho H. And again, here we are saying that H2 on this side, it is much, much smaller because we are saying that this opening is very, very close to the bottom. So height 2 can be approximated also to 0. So if you are able to insert it at that point, our equation now can be able to, you can be able to see the values, A1, A and A cancelling out, rho and rho cancelling out. So we are just going to remain with V2. So V2 is going to be the square root of 2GH. So that one you can be able to see that if you have it's basically the square root. So we have, if you make V2 to be the subject, it will be the square root of what? 2GH. So if you just take this to the right hand side here, basically there is no, these two will be able to come to this side, and you'll be able to get velocity 2 being given by this equation. So the equation shows that the velocity of the liquid flowing out only depends on the height of the liquid, but not on the radius of the opening. So some applications of the Bernoulli's equation, we have the flow meters. Flow meters, we have the venturi meter and the pitot tube. We also have what you call jets and nozzles. Then you have what you call the dynamic lift. So here we're going to look at the spinning ball and the aerofoil, or the thrust in a rocket. So we're going to look at some of these applications and see clearly how Bernoulli's equation is applied in them. So the first one you're going to look at is the venturi meter. The venturi meter is just a device which has a throat, something which we are calling a throat here. Basically, these are different cross-sectional areas. And so it has an inlet, it has an outlet. So when the liquid is flowing, there is going to be clearly a change in pressure. We know very well from the equation of continuity that when the liquid is flowing, when it moves from a large cross-sectional area to a smaller cross-sectional area, there's going to be a change in velocity. So the velocity is going to increase. And you know that when the velocity increases, the pressure decreases. The pressure decreases. So you can be able to see that there's a lower height on this end here. Since the velocity is lower, the pressure is higher. So this pressure difference is actually what is used in the venturi meter to be able to calculate the flow rate of the liquid which is flowing in the venturi. So the working of the venturi meter is explained here. Whereas the water enters into the throat, the velocity increases and the pressure therefore drops to the minimum. The pressure difference at the two sections can now be seen in the manometer attached at both sections. So basically, if you can be able to attach a manometer here, or even these two can just behave as a manometer, where basically the height difference between these two can be able to be proportional to the velocity or the flow rate at which the liquid is flowing. So you're going to come up with an equation using Bernoulli's equation, where you have P1, so you can be able to see this equation here. This is the Bernoulli's equation, where basically Z1 represents the level, because it represents the level of the liquid flowing in the tube. So Z1 is kind of the diameter of the wide tube. Z2 is the diameter of the narrow tube. So if we just put the pressures, if we put these values, P1 and P2, we put them on one side, on the left-hand side, and then the velocities, you also put them on the right-hand side, as you can see from equation 1. Then we can be able to make H to be the subject, where basically here P1 minus P2 or divided by rho g is the difference of pressure heads at section 1 and section 2. So the whole of this one here can be represented by our H here. So it can be able to be seen that our height difference, which you can be able to see here, this H is what you're talking about. That height difference will be equal to the pressure difference, that is P2 minus P1 divided by rho H. So you have said the whole of this is equal to H. And therefore, H, which is the height
Excuse
difference.
me, sir.
Yes?
I have a question.
Go ahead.
The presentation is not that clear.
Uh-huh.
Yeah, so
it's not clear. Good. So if we can be able to see, our height will be equal to V2 squared minus V1 squared over 2G. So we can be able to, in this venturi meter, if we know this height difference here, we can be able to get the speed at which the liquid is flowing. So a venturi meter is a meter which is also used like in the water supply stations to be able to measure the speed at which the water is flowing, just by making use of the height difference between the two sections. And we have tried to explain how the venturi meter works. So let me go ahead and, so if you apply the equation of continuity at section 1, equation of continuity, it's A1 V1 is equals to A2 V2. If you apply this equation of continuity, we can make V1 to be the subject, which will be given by this. And then we can be able to substitute this equation of velocity in equation 2. Our equation 2, remember it was here. And so if you substitute for V1, you can be able to get velocity 2 will be given by this into square root 2gh. And this one again confirms the fact that velocity is not dependent maybe on the pressure, but just the height of the liquid level in that particular pipe. The second application is the pitot tube. Basically, the pitot tube, you can be able to see it works on the level of water which is flowing through a particular tube. And then you insert what you call a stationary point or a stationary object. So as you can be able to see here, this is a very narrow tube. So this narrow tube here, as the liquid flows, basically because of the narrowness of the tube, the velocity is going to really decrease at this particular point because of the narrowness as it's trying to enter here. And so as the velocity decreases, then the pressure is going to increase at this particular point here compared to this region. There is a place which we call stagnation point where almost the velocity tends towards zero because of the introduction of like a barrier into this particular tube. So when the velocity, as the velocity is decreasing, then the pressure increases. So again, this pressure difference, this height difference between the static pressure and the stagnation pressure can be converted into a velocity or what you're calling the flow rate. You can be able to use it to calculate the flow rate. And the explanation is here. Basically, I try to give the explanation. When the solid is kept centrally, the stationary in a pipeline with a flowing fluid, the velocity of the fluid starts reducing due to the presence of what? That body. So that reduction in velocity will correspond to an increase in pressure due to the conversion of kinetic energy to pressure energy. And so that pressure difference can be used to be able to measure the speed at which the liquid is flowing using the area equation here. This equation which we're able to write, we were able to derive from at this particular point. So other applications of Bernoulli's effect is the dynamic lift. Basically here we look at streamlines. And I think here the emphasis is the rate at which streamlines are flowing on the upper side and on the lower side, and also the direction of the spinning of the ball. So, for example, if it is here, it is spinning in a clockwise direction. So therefore, the upper streamlines will move at a higher speed, therefore lower pressure, and the lower streamlines will move at a lower speed due to that kind of opposition of the movement of this object. So that pressure difference will bring about what we call a dynamic lift, a force which will tend to lift it upwards. Another one is the aerofoil. Aerofoil is basically an object which is shaped in this manner, which has been shown, and in such a way that the streamlines, if it's moving against the wind or the flow of the air, then the air flow will flow faster on the upper side due to the streamline shape of the object than also the ones on the lower side. So when the aerofoil moves against the wind, the orientation of the wind relative to the flow direction causes the streamlines to crowd together at a particular point, and the flow speed on the top will be higher than that which is below it. Thus, an upward force will result in the dynamic lift of the wings. Like the air part, the parts of an aeroplane, they are shaped, they have the shape of an aerofoil. So one more thing which you're going to look at before we conclude is the flow of a liquid through a narrow tube, what you call the Boycella's formula. This one is now going to just put together the two formulas you have been learning. Number one, we look at the following. These are the assumptions which are being made. You can be able to see the assumptions. And then in this formula here, we basically have two pipes. There's an outer pipe and there's an inner pipe. Poiseuille's formula tries to look at the speed at which a liquid is flowing. There are two forces which are making the liquid to flow. One of them, it is the pressure difference. When the liquid is flowing, a liquid can be able to flow if the pressure at one point is higher than the pressure at the second point. The other thing now we have is viscosity. We have been able to look at the formula of viscous drag. We're able to see that viscous drag will be given by, according to Newton's law of viscosity, it was force per unit area. So if you make force to be the subject, the viscous drag will be given by thou multiplied by area. And thou, according to the dimensional analysis, we're able to find that it's given by this formula here. Then the cross-sectional area, or the area of this, where the liquid is flowing, the surface area will be 2 by r multiplied by the length. So that's our equation number one. Then another important formula which you can be able to see in the equation number two, it is now the pressure, what you call the excess pressure. So the excess pressure will also be, the force resulting from that will be pressure multiplied by area. So you can be able to see the area being by r squared. So from there, when you sum up these two forces, they should be able to be equal to 0. And they should be able to be equal to 0. And then now,